Srimati R. Padmavati, Head of Department ECE, Dhanalakshmi Srinivasan College of Engineering and Technology, Chennai. She pursued her Bachelor of Engineering in Electronics and Instrumentation Engineering at the National Engineering College, Kovilpatti. She then went on to work as a technical editor in Domix Technical Information Private Limited, Chennai. She then pursued her Masters of Engineering in Applied Electronics at Satyabama University, Chennai. She is currently pursuing her PhD in Anna University, Chennai. She has published several national and international journals and has attended many conferences. Her areas of interest include linear integrated circuits, digital electronics, electronic circuits, VLSI design.
Welcome to UGC lecture series on BSc Electronics Honors Analog Electronics. Today we are going to learn about the introduction to PN junction, phenomena occurs during formation of a PN junction, formation of PN junction, biasing PN junction diode and VI characteristics of PN junction diode. First let us see the introduction to PN junction. Whenever we have decided to learn electronics, we have to start from the diode. For the diode, the basic building block is PN junction, and the diode is the basic building block of any electronic system. It plays a vital role in electronic systems. Its characteristics are closely matched with the switch. Its applications are ranging from simple to very complex. How a PN junction is formed? Generally, all the elements are classified into conductors, semiconductors and insulators based on their electrical conductivity. Conductors have high electrical conductivity and insulators have very least electrical conductivity, and the semiconductors have electrical conductivity in between the conductors and the insulators. The general common semiconductor materials are germanium and silicon. The germanium and silicon semiconductor as pure semiconductors, we cannot use this pure semiconductors because the electrical conductivity is very low at room temperature. So, we have to increase the electrical conductivity. How we can increase the electrical conductivity of this pure semiconductor material, germanium or silicon? We can also say the pure material as intrinsic semiconducting material. And how this intrinsic semiconducting material will have high electrical conductivity? By using a concept called doping. What is doping? It is a process of adding impurities to a pure semiconducting material. So, if we add a pentavalent impurity, that is a number of valence electrons is 5, to a pure semiconducting material, maybe a germanium or a silicon, we can obtain an N-type extrinsic semiconductor material. And if we add a trivalent impurity, that is the number of valence electrons is 3, to a pure semiconducting material, germanium or silicon, we will get a P-type semiconducting material. It is an extrinsic semiconducting material. Now, these extrinsic semiconducting materials are useful for any electronic system because its electrical conductivity is increased by the process of doping. Doping is a process of adding impurity to a pure semiconducting material. So, we have two types of extrinsic semiconducting materials called P-type and N-type. So, this is a simple block of P-type and N-type semiconductors. So, this is a N-type semiconductor which has majority carriers as electrons and minority carriers as holes. Electrons are negatively charged particles and holes are positively charged particles. So, for N-type, the negative charged electrons are the majority carriers and positive charged holes are the minority carriers. For P-type, it is reverse. The majority carriers are holes and the minority carriers are these electrons. Next, what are all the phenomena occurs during the formation of PN junction? So, this is very important for PN junction diode also. So, first one, diffusion and formation of space charge and drift. So, how we will form a PN junction is very important. So, first we have to take a semiconducting material, germanium or a silicon. It is very pure and we want to increase the electrical conductivity. So, we have to dope a impurity to the semiconducting material. So, when we dope a pentavalent impurity, we will get n-type semiconducting material, because in n-type the number of electrons is high. So, we are taking a silicon base to which we are adding a pentavalent impurity. So, we are obtaining a n-type semiconductor, and with the same semiconductor base, we are adding a trivalent impurity to obtain a p-type semiconductor. Now, we are having an n-type semiconductor and p-type semiconductor on a single semiconductor, pure semiconductor base. So, now the p-n semiconductors are joined together. So, once the p-n junction is formed on a semiconductor material as a base, what will happen is the charge or the electrons from n side will move towards the junction or diffuse through the junction to the p side region, and similarly the holes from p side diffuse through the junction and moves towards the n side region. This is the initial current, initial movement of the charge carriers from n to p and p to n, and this is said to be diffusion, because the electrons diffuse through the junction and holes from p side also diffuse through the junction. So, here because of the movement of this electrons and holes, we will have a current flowing through the diode. This current is said to be diffusion current. Here it is given in this arrow mark, diffusion force on holes. So, here holes from p side will move towards the n side region through the junction, and this is diffusion force on electrons. So, electrons from n side will diffuse through the junction towards the p side region. So, this is the arrow mark which indicates the flow of holes and flow of electrons, and this current is said to be the diffusion current. And next we have to see the space charge formation, how the space charge is formed. Because of the movement of the electrons and the holes, we are getting the charge carriers accumulated near the junction. For example, if you see the electrons from n region will move towards the p region, it will leave positive charges near the junction, and from p side also, when holes move towards the n region, it leaves negative charges near the junction. So, what will happen? The negative charges are accumulated and the positive charges are accumulated near the junction. So, because of these charge carriers accumulated, we are having a space charge region here. Otherwise, it is known as depletion region. Why it is called so? Depletion. Why it is called as depletion region? It is because the electrons from n side depleted their original position and leaves behind the positive charge. Also, the holes depleted their original position and leaves the negative charge. So it is known as depletion region. Because of this depletion region, we will get the electric field in the depletion region, and this electric field is opposite to the movement of the diffusion current. See, the arrow mark is from positive to negative. So, this electric field is from positive charge to negative charge. Due to this electric field, the electrons in the p side will move towards the n side and holes in the n side will move towards the p side. That is what given here. Electric field force on holes. Holes from this n region move towards the p region, and this is electric field force on electrons. So, here the electrons from p side will move towards the n side. So, the current direction, the flow of charge carriers is opposite to that of the diffusion current. So, this movement of charge carriers due to the electric field is said to be drift current. Movement of charge carriers due to the electric field is said to be drift current. So, drift current is an opposite of the diffusion current. Initially, the diffusion current is very high and drift current is very low. So, the diffusion is due to the initial movement of the charges, and because of the diffusion we will get a space charge formation near the junction, and due to the space charge formation near the junction we will have an electric field. Because of the electric field the charges move from N to P and P to N. Because of this drifting of charges we are getting the drift current. Note that the drift current is an opposite direction to the diffusion current. Next, the formation of p-n junction. So, can you say out of these three phenomena, diffusion, depletion and drift, which one happens first during the formation of p-n junction? It is obviously the diffusion, because once the p-n junction is formed, the diffusion of charge carriers across the junction forms a depletion region at the junction. Then the depletion forms the electric field, and this electric field results in drift. So, initially diffusion current will be the highest and drift current will be very, very small. Gradually the depletion region formation continues, drift current builds up and diffusion current falls down. There comes a particular point of time when diffusion current is exactly equal and opposite to the drift current, and junction comes to a state of equilibrium. At this state there is no net current, and hence the formation of p-n junction is complete. So, when the net current is 0, when the depletion region formation continues, the drift current builds up, that is the drift current will be increased and the diffusion current will be decreased. At one point of time the diffusion current and the drift current are equal and opposite in direction, so the net current is 0. At this state the p-n junction is complete, and this is said to be in equilibrium condition. How it is maintained? How the equilibrium is maintained? The electrons have moved from n side to p side during the diffusion. So, during the diffusion electrons will move from n side to p side and holes will move from p side to n side. So, the n region has lost its electron, where p side has gained electrons. So, n region, when we compare the potential, the n region has positive charge than the p region, because the n region loses its electron and p region gains the electron. So, the potential there arises the potential difference across the junction. How the equilibrium is maintained? It is because the electrons have moved from n side to p side during the diffusion. So, n region has lost its electrons and p region has gained its electrons. So, the n region is more positive than the p region if we compare the n region and the p region. So, there results in potential difference across the junction. At the state of equilibrium, this potential difference reaches a particular state that it prevents any further flow of electrons from n side to p side. To overcome this potential difference, we have to apply an external voltage more than the potential difference, and so the electron will move from n region to the p region. But without any external voltage, the p-n junction kept alone will not be able to move any single electron from the negative region to the positive region. So, this state is said to be equilibrium state, and thus it is maintained with net current 0. And this potential difference is otherwise called as barrier potential, because it forms a barrier for the electron movement from n region to the p region. p-n junction has a barrier potential only when we apply external voltage above the barrier potential, then the diode will conduct. This simply means the current will pass through the p-n junction only if we apply an external voltage more than the barrier voltage. To apply an external voltage, we usually connect two metallic contacts on either side of the p-n junction. If we connect the metallic contacts on either side of the p-n junction, then it is a semiconductor diode or a p-n diode. So, this is the symbol of p-n junction diode. Here it is a p-type region and this is n-type region. So, these two lines are the metallic contacts. So, once the metallic contacts are given to this PN junction, this becomes a diode now, and this arrow represents anode and this bar represents the cathode. This is the symbol of PN junction. Here the movement of electrons and the holes has been represented. Biasing PN junction diode. The process of applying an external voltage is called biasing. There are two types of biasing, forward bias and reverse bias. So, why we want to go for biasing is, we have to apply an external voltage above the barrier voltage for the movement of the electron from N side to P side. So, we want to give a bias. So, in this bias we have two conditions, forward bias and reverse bias. The basic difference between the forward and reverse bias is in the direction of applying external voltage. First we will see the forward bias of PN junction diode. Okay, here this is the p-type material and this is the n-type material. See, this is the external voltage applied, VEXT, external voltage. The positive terminal of the external voltage is connected to p-type and negative terminal of external voltage is connected to n-type. And what is here? It is the depletion region or space charge region. It has negative charges and positive charges accumulated near the junction. Because of the accumulated charges, we have the electric field which is opposite to the external applied voltage. So, in the forward bias, the electric field or external voltage applied is in the direction opposite to the electric field generated in the depletion region. So, the barrier potential is different for different semiconducting materials. Here for the silicon it is 0.7 volts and for germanium it is 0.3 volts. So, if we take a silicon semiconductor, we have to apply voltage more than 0.7 so that the diode will conduct. Okay, we will consider silicon semiconductor material in our case. This is the voltage current characteristics of PN junction diode. So, once the forward bias is given for the diode, we have to increase the voltage across the diode and see what happens for the current through the diode in the case of forward bias. So, this is our requirement here. Here we are increasing the voltage, but there is no change in the current, it is 0. So, current has been taken along the y axis and voltage along the x axis. In the forward bias, the current range is in milliamps, it is not mentioned here. So, once the voltage is increased, applied voltage is increased up to the breakdown voltage, up to the barrier potential, there is no change in the current. And after the barrier potential, if we increase the external voltage, the current is gradually increased with the external voltage. This is what happened when the PN junction diode is given a forward bias. So, how it happens? See, the 0.7 is the barrier potential for silicon. So, this VD is the barrier potential. So, from 0 volts to 0.7 volts, if we apply external voltage, there is no current because there is a depletion region. This is the depletion region, and consider the width of the depletion region is W, and the width is W when the external voltage is 0, and width is 0 when the external voltage is 0.7. See here, if the width is 0, then the current will flow through the diode because we have cancelled the depletion region through the external voltage application. So, the barrier potential of silicon diode is 0.7. The diode starts conducting at 0.7 volts and current through the diode increases linearly with increase in voltage. So, for the forward bias characteristics of a PN junction diode shows the diode conducts current linearly with increase in voltage applied across the two terminals. What happens inside the diode? Okay, we have seen the VI characteristics of a PN junction diode, and we have seen the current circuit connection. Now what happens inside the diode when we apply external voltage as a forward biasing? Okay. So here this is positive and the p-type material has holes in it, and here this terminal is negative and n-type material have electrons in it. We know that the electrons are negatively charged particles and the holes in the p-type are, electrons are negatively charged and holes in the p-type are positively charged. So here is positive and the majority carriers of p-type is also positive. So due to the force of repulsion, what happens is the holes in the p side will move towards the junction, and here this is negative and the majority carriers in n-type is also negative. Again, due to the force of repulsion, the electrons will move towards the junction. So this cancels the width of the depletion region, and further if we increase the external voltage, again more number of electrons will move towards the junction, more number of holes will move towards the junction, thus the width will get reduced and thus the flow of electrons will happen. Flow of electrons and holes will happen, and this causes the current flowing through the diode. This means the depletion region vanishes at 0.7 volts of applied voltage, thus results in increased diffusion of electrons from n side to p side region and increased diffusion of holes from p side to n side region. How the current flow takes place in a p-n junction diode? As we said earlier, as the voltage level increases, the electrons from n side gets pushed towards the p side junction. Similarly, the holes also from p side to n side junction. Now there arises a concentration gradient between the number of electrons at the p side junction region and number of electrons at the region towards the p side terminal. So here, if due to the force of repulsion, the holes will move towards the junction. So it will create a electron. We know that if electron is moving from one place to another place, it will create a hole. And similarly, when a hole is recombined with the electron, it will produce a negative charge. So once the holes are moving towards the junction, it has the negative charges here. So more number of holes moving towards the junction creates negative charges near the junction. So there exists the concentration gradient between the charges near the junction and at the terminal of p-type, and also the holes near the junction and at the terminal of n-type. So because of these charge concentration, variation in the charge concentration, the flow will takes place. The movement of the charges will takes place, and due to this the current flow exists in the forward bias condition. And next is reverse bias condition of p-n junction diode. How the reverse bias is given for a p-n junction diode? So what we have seen in the forward bias is we have applied a positive terminal. We have applied a positive terminal of the external voltage to the p-type. Here this is the external voltage applied to the diode, and consider this as a semiconducting material. So here I have connected the negative terminal. So what comes here? We have to reverse the direction for the reverse bias, isn't it? So here p-type and here n-type. So the positive terminal is connected to n-type and negative terminal is connected to p-type. What is this? This is the depletion region. This is the depletion region. Here negative charges are accumulated, here positive charges are accumulated as we discussed earlier. Because of this accumulated charges, the electric field will be produced, due to which the drift current will takes place. So this is the V external. So the negative terminal is connected to the p-type and positive terminal is connected to the n-type. This is the circuit diagram of the reverse bias of p-n junction. In reverse bias, the external voltage which is opposite in direction to the forward bias. So, here we connect the positive terminal of battery to N side and negative terminal to P side. This completes the reverse bias circuit. And when we see the VI characteristics of the reverse bias, here we have seen this is the forward bias characteristics and this is the reverse bias VI characteristics of a PN junction. As I said, for the forward bias, the current range is in milliamps, but for the reverse bias, the current range here is microamps. In the forward bias only, the diode will conduct. In the reverse bias, the diode will not conduct, and this current is very negligible and almost constant. Maybe you can say it is in the range of microamps. So, from 0 to some extent, if we increase the voltage, the current flow is very negligible. It is not given in the scale, but it is very negligible, maybe in the range of microamps or nanoamps. And after which, if you increase the voltage, say for example 80 volts or 90 volts, if you increase the applied voltage, suddenly the current will increase. And this voltage at this point, if the current increases suddenly, and this voltage is said to be a breakdown voltage, and this current is said to be reverse current or reverse saturation current. This is the VI characteristics of the diode in reverse bias condition. So, this is very important, this breakdown voltage. Every diode has a maximum limit of current it can withstand. If we apply a voltage more than very high voltage, then if it does not withstand the current, then the diode will get damaged or burnt in the reverse bias condition. So, what will happen inside the diode? What will happen inside the diode is, here we have applied negative charge and the majority carriers of the p-type material is whole, these are positively charged. Here we have connected negative and here we have positive charge. Similarly, here positive and the majority carriers have negative charge. So, this is force of attraction. In the previous case, we have seen force of repulsion. Here this is force of attraction. So, all the holes present in the p side will attracted towards the negative terminal and the electrons present in the n side will get attracted towards the positive terminal, and so the depletion region width will become very high, say from W to W plus X. X is the width increased due to the reverse bias. And if the depletion region width is very high, then the electric field is also exist. Due to this electric field, the drift current will takes place. There is no diffusion of electrons and holes, so the diffusion current is 0 and drift current only takes place during the reverse bias condition. How the reverse saturation current occurs and why it exists? The reverse saturation current is the negligibly small current from 0 volts to breakdown voltage. It remains almost constant in the range of 0 volts to reverse breakdown voltage. As electrons and holes are pulled away from the junction, they do not get diffused each other across the junction. So, the net diffusion current is 0. The remaining is only the drift current due to the electric field. So, at breakdown, the current through the diode shoots rapidly. Even for a small change in the applied voltage, there is a high increase in net current through the diode. For each PN junction diode, there will be a maximum net current that it can withstand. If the reverse current exceeds this maximum rating, the diode will get damaged. Conclusion about the PN junction characteristics. So, in a PN junction diode conducts current only in one direction during the forward bias. The diode conducts current with increase in voltage in forward bias, and diode does not conduct with increase in voltage in the reverse bias. The breakdown usually results in damage of diode. So, we have come to the summary. So, we have seen introduction to PN junction. What are all the phenomena occurs during the formation of PN junction, that is diffusion, space charge formation or depletion, and drift, formation of PN junction, and biasing of PN junction, forward bias and reverse bias, and voltage and current characteristics of PN junction diode. So, these are some of the questions, you can recollect the answers. what is diffusion current, how the drift current flows in the diode, why do we need to bias a PN junction diode, and what happens when the voltage is increased beyond the breakdown voltage. Diode is working as a switch, justify either way. Thank you.